Did scientists create a universe without time? What cold atoms reveal about the birth of time? Imagine removing every clock around you. Take down the clock on the wall. Turn off your smartphone. Hide the clock on your computer. Now go a little further. Imagine that you can no longer see the sunrise or set. You cannot observe the rotation of the Earth. You cannot even feel the rhythm of your own heartbeat. Would time disappear? We instinctively think that time exists first. Time flows like an enormous river, and everything else happens within it. We are born in that river. We grow older in it. Stars are born and die in it. Galaxies evolve within it. But when we descend into some of the deepest questions in modern physics, we encounter a very different possibility. What if time was never there in the first place? What if time emerges only from the relationships between one change and another? In 2026, physicist Giovanni Barontini at the University of Birmingham brought this ancient question into the laboratory in a remarkable way. He did not observe the entire universe. Instead, he used tens of thousands of ultracold atoms to create something like a tiny model universe. And then he asked that miniature universe a very unusual question. If there is no clock outside you, can you create your own time? When time disappears from physics? To understand this experiment, we first need to encounter one of the strangest problems in theoretical physics. It is called the problem of time. For Isaac Newton, time was simple. Time existed independently of everything else. Whether an apple fell from a tree or nothing moved at all, time would continue to pass. Even if the entire universe suddenly froze, Newton's absolute time would continue ticking somewhere in the background. Then Einstein changed the story. In relativity, time is no longer an invisible universal clock outside the universe. Time depends on motion. It depends on gravity. Clocks moving at different speeds can disagree. Clocks located in different gravitational fields can disagree. Time became part of space-time itself. But when physicists attempted to combine general relativity with quantum mechanics, something even stranger appeared. In the canonical approach to quantum gravity associated with John Wheeler and Bryce DeWitt, the equation describing the quantum state of the entire universe contains no ordinary external time parameter. The universe is described fine, but the familiar clock seems to disappear. And this creates a profound question. If there is no external time, how does the universe change? How can we say that the Big Bang came before galaxies? How can we distinguish earlier from later? If there is no giant clock sitting outside the universe, what tells the universe what time it is? Perhaps the problem lies in the way we ask the question. Think about a character inside a novel. That character does not need the wall clock in the author's room. For the character, time is defined through relationships between events. One chapter comes before another. A meeting happens before a farewell. A decision comes before its consequence. Perhaps the universe works in a similar way. Perhaps time does not need to flow from somewhere outside the universe. Perhaps time can be defined by asking, when one thing changes, how does another thing change in relation to it? This idea is known as relational time. Can part of the universe become a clock? The basic idea of relational time is surprisingly intuitive. If the universe has no external clock, then perhaps one part of the universe can serve as a clock for another. You might track how the position of one object changes while another object evolves. Or in cosmology, one field might act as a clock while the size of the universe changes relative to it. Instead of asking, how many seconds have passed? We ask, when this variable changed by this amount, how much did that variable change? But there is a problem. A physical quantity used as a clock may not always move in one direction. Imagine using the position of a pendulum as your clock. The pendulum moves right, then comes back left. The same position appears more than once. So if all you know is where the pendulum is, you may not know whether it is moving forward or returning. A recollapsing universe has a similar problem. A variable may increase during expansion and then decrease during contraction. The same value can appear twice. So physicists have long faced a difficult question. What can serve as a reliable internal clock for an entire evolving system? This is where Barontini's cold atom experiment becomes fascinating. A tiny universe made from 24,000 atoms. The experiment used about 24,000 rubidium-87 atoms. The atoms were cooled to extraordinarily low temperatures. Under these conditions, something remarkable happens. Instead of behaving like many independent particles, the atoms begin to behave collectively, almost like one giant quantum wave. This state of matter is called a Bose-Einstein condensate, or BC. Barontini placed this condensate inside an optical trap created with laser light. Then he introduced a thin optical barrier. The barrier divided the system into two regions. One region was called the bright sector, the part being observed. The other was called the dark sector, the part treated as unobserved. The total atomic system remained extremely well isolated during the experiment. But if we focus only on the bright sector, something interesting happens. Atoms can cross the barrier. They can enter the bright sector and later leave it. The researchers treated this bright sector as a kind of miniature universe. When atoms first entered the bright region, the event was described metaphorically as a Big Bang. The atomic cloud then expanded. It reached a maximum size. Then it contracted again. Eventually the atoms returned toward the dark sector, a miniature analogue of a big crunch. Then another cycle could begin. Now this needs to be stated carefully. The researchers did not recreate the actual Big Bang. They did not reproduce the full gravitational physics of our universe. This is an analog system. Certain dynamical variables in the condensate are mapped onto variables that appear in simplified quantum cosmology models. The point is not to build a literal universe in the laboratory. The point is to create a controlled physical system in which questions about relational time can actually be tested. The atomic position was not a good clock. Within this miniature universe, the center of the atomic cloud can play a role similar to a clock variable. But the cloud oscillates. It moves in one direction and then comes back. So the same position appears again and again. Just knowing the cloud's position does not tell us whether this mini-universe is expanding or contracting. This resembles a problem that appears in recollapsing quantum cosmology. So Barontini looked for another clock, and the quantity he chose was surprising. It was entropy. When entropy becomes time, we often hear entropy described simply as disorder, but that word can be misleading. A better intuition is that entropy is related to how many microscopic configurations can correspond to the macroscopic state we observe, and therefore to how much microscopic information is unavailable to us. In Barontini's experiment, the entire system was nearly isolated. If you combine the bright sector and the dark sector, the total entropy remained approximately constant within experimental uncertainty. But the entropy of the bright sector alone could change. Why? Because atoms were moving between the two sectors. The total system could conserve entropy, while entropy flowed from one subsystem to another. And Barontini used this internal entropy exchange to construct a new kind of clock. He called it entropic time. Instead of measuring time using an external laboratory clock, he measured the ordering of events through changes in the entropy of the observed sector. And something remarkable happened. The atomic position moved backward and forward. But the entropic time could still order most of the evolution in a consistent direction. Even more interestingly, this internal time did not always flow at the same rate. When entropy was being exchanged strongly between the bright and dark sectors, entropic time advanced more rapidly. When almost no entropy was being exchanged, entropic time barely advanced. And this leads to one of the most striking parts of the experiment. After one analog, Big Crunch, and before the next analog, Big Bang, ordinary laboratory time clearly continued to pass. The clock on the laboratory wall kept ticking. The computer kept recording time. But if almost no entropy was exchanged between the two sectors during that interval, almost no entropic time passed inside the miniature universe. This is a deeply unfamiliar picture. The external clock continues to move. But from the internal perspective of that system, almost nothing happens. So we return to the original question. If nothing changes, in what sense has time passed? Rebuilding quantum dynamics without an external clock. The importance of this work goes beyond simply labeling entropy as time. Barontini did something more demanding. He used this internally constructed entropic time to describe the actual quantum dynamics of the condensate. Conceptually, the procedure is almost paradoxical. First, remove the external laboratory time from the description. Then construct an internal clock from entropy exchange. Then use that new clock to predict how the atomic cloud should evolve. Finally, compare those predictions with experimental measurements. The calculated evolution successfully reproduced the observed expansion and contraction of the condensate. So this was not merely a philosophical metaphor. The researchers showed that an experimentally defined internal time could be used to quantitatively describe real dynamics in the laboratory. Did this experiment discover the true nature of time? Here we need to be careful. This experiment did not prove that time is entropy. It did not prove that the Wheeler-DeWitt equation is the final theory of quantum gravity. And it certainly did not create a real universe inside a laboratory. What it demonstrated is much more specific. In a controlled quantum system, an internal time constructed from entropy exchange can reliably order physical events, and dynamics expressed in terms of that internal clock can reproduce experimental observations. That distinction matters. But precisely because the claim is limited, the experiment is scientifically important. Questions that once belonged almost entirely to philosophy and highly abstract quantum gravity theory are slowly becoming questions that can be measured, compared, tested, and potentially falsified. Is time a thing or a relationship? Now let's move for a moment beyond the experiment. Think about the way we remember our own lives. We do not remember our lives in seconds. Most of us do not remember what happened at exactly 3:27 p.m. on a random afternoon 10 years ago. Instead, we remember events. The first time we met someone, the day we left school, the moment we lost someone, the instant we understood something that changed the way we saw the world. Human memory organizes time through relationships between changes. Of course, human memory is not the same thing as physical time, but the analogy helps us understand relational time. Newton's time was like an empty stage. The actors could leave, but the stage remained. Einstein changed the stage itself. The stage could stretch, bend, and behave differently for different observers. Some approaches to quantum gravity ask an even more radical question. What if there was never a stage at all? What if what we call the stage emerges only from relationships among the actors? Barontini's cold atoms do not answer that question, but they show that we can begin turning the question into an experiment. And this brings us to another possibility, an information gauge interpretation. From this point onward, we need to clearly separate the original experiment from a further theoretical interpretation. What follows is not a claim made by Barontini's paper. It is a possible extension from the perspective of an information gauge or IG framework. The experiment contains a very interesting structure. The total atomic system is nearly isolated, but atoms move between the bright and dark sectors. Entropy moves between them. The observable information describing the subsystem changes. From an IG perspective, this entropy exchange could be treated as an experimentally accessible proxy for something like an information current. That does not mean entropy and fundamental information are identical. It simply means that entropy flow provides a measurable handle on information transfer between subsystems. From this point of view, entropic time may not need to be interpreted as the deepest form of time itself. It may instead be one particular relational clock constructed from information flow, and then IG asks an additional question. What if information is characterized not only by how much of it moves, but also by the path through which it moves? What if the history of the path can leave a measurable physical trace? What if a closed path leaves a quantum trace? There is a beautiful concept in physics. A system can travel through a sequence of states and eventually return to where it started. The beginning and ending macroscopic states may look identical, and yet the route taken through state space can sometimes leave a phase behind. In broad terms, this kind of path-dependent residue is related to the idea of holonomy. Barontini's experiment is particularly interesting from this perspective because the condensate naturally undergoes repeated cycles. An analog Big Bang, expansion, contraction, an analog Big Crunch, and then another cycle. So the system can trace a loop through its reduced state space. Now imagine performing a more phase-sensitive version of the experiment. Before and after one complete cycle, suppose that the atom number is the same, the position is the same, the cloud size is the same, and the entropy is nearly the same. Macroscopically, the system has returned to where it began. But now measure the quantum phase of the condensate. What if a tiny phase difference remains? That alone would not prove new physics. Atomic systems accumulate many ordinary phases. There are dynamical phases, trap-related phases, mean field interaction effects, known geometric phases. All of those would have to be calculated and removed. But if a reproducible residual phase remained after all known contributions were accounted for, then it would become interesting. Reverse the path. There is an even stronger test. Run the cycle in one direction. Then design another protocol that traverses the corresponding path in the opposite direction. Suppose the forward cycle produces a small positive residual phase, and the reverse cycle produces an equally small negative phase. That would be far more distinctive than simply finding an unexplained offset. An instrumental drift does not automatically reverse sign when the path direction is reversed, but a genuinely orientation-dependent holonomy should. This gives us one of the clearest possible IG signatures. Forward path, positive residual. Reverse path, negative residual. Not merely an anomaly, but a very specific symmetry pattern. The optical barrier becomes a control knob for information flow. This platform has another powerful feature. The height of the optical barrier separating the bright and dark sectors can be adjusted. Lower the barrier, and atoms can move more easily between the sectors. Entropy exchange becomes stronger. Raise the barrier, and the exchange becomes weaker. From an IG perspective, this is extremely useful. If an additional phase is genuinely related to information transport, then changing the barrier should not produce arbitrary changes. The residual phase should vary systematically with the amount of entropy or information proxy being exchanged. So the experiment could control three things at once: the barrier, the entropy flow, and the residual quantum phase. If all three show a reproducible correlation, the case for a new effect becomes much more compelling. Can we run time forward and then undo it? The original paper also points toward a possible future experiment using a Loschmidt echo. The name sounds complicated, but the idea is intuitive. Imagine filming a ball, rolling across a table and knocking over a cup. Now run the video backward. The cup rises. The ball returns. Everything appears to go back to its initial state. In quantum physics, one can attempt something conceptually similar. Let the system evolve forward. Then reverse the dynamics as accurately as possible. Finally, ask how closely the system returns to its starting state. If everything is perfectly reversible, the initial state should be recovered with very high fidelity. But if there is an additional path-dependent structure, then even when the system appears to return to its original macroscopic state, a tiny phase or echo residual might remain. Again, this is not something discovered in the current experiment. It is a possible future IG null test, and that distinction is crucial. A new theory does not become science merely because it can explain something afterward. It becomes scientifically useful when it tells us what measurement could prove it wrong. Does the universe remember the path it took? In the end, all of these ideas can be reduced to one remarkably simple question. Does the universe remember the path it travelled? If the present physical state is exactly the same, does all information about the route to that state disappear? Or can a subtle physical trace remain? Standard physics already contains path-dependent phenomena. There are geometric phases, there is hysteresis, there are environmental memory effects. So an IG interpretation would only become meaningful if it produced a pattern that could not be absorbed into those known effects. That is why the strongest strategy would not be to search for one strange number. Instead, we would ask whether several signatures appear together. Does the residual change sign when the path is reversed? Does it scale with controlled entropy exchange? Does it accumulate reproducibly over repeated cycles? Does the same effect appear in a Loschmidt echo? If all of those conditions were satisfied simultaneously, then we might have reason to investigate a deeper information gauge structure. And if nothing is found, that result would still matter. It would place an upper bound on how strongly such an information gauge effect could couple to the system. A null result can also teach us something about nature. Does time flow or is it made? We often imagine time as a river. It begins somewhere in the past, passes through the present, and flows toward the future, and we imagine ourselves as small boats carried along with it. But Barontini's cold atom universe suggests another picture. Inside that miniature universe, time does not need to arrive from somewhere outside. Atoms and entropy move between subsystems. States change relative to one another, and from those changes an ordering of events can emerge. The information gauge perspective adds one more question. Could those connections contain not only an ordering, but also a memory of the path? After travelling around a full loop and returning to the same place, does the universe somehow know where it has been? We do not yet know the answer. Perhaps time is one of the most fundamental ingredients of reality. Or perhaps time is an emergent phenomenon arising from structures deeper than we currently understand. But something important has changed. Not long ago, the question, what is time, belonged mainly to philosophers and to equations written on the blackboards of quantum gravity theorists. Now we can cool tens of thousands of atoms, shape their world with laser light, watch them exchange entropy, and ask them the same question, what is time? And perhaps the answer will not come from building a more accurate clock. Perhaps it will come from understanding more deeply how change and information are connected and what traces those connections leave behind. Maybe time is not something that simply flows. Maybe time is the way changes read one another. This has been Thoth Saim's Science Cat.